Welcome everybody. I am super excited to be kicking off this quantum software talk series from the Unitary Fund. Um, my name is Dr. Sarah Kaiser. I do a bit of Twitch streaming here and kind of thought it would be a really cool place to actually talk about quantum software. Um, so, oh yay, thanks for me. So today we're going to hear from Dan Strano, who works on an open source quantum software project called Qrack, and that for quantum simulation, and not just any simulation, very fast. Let me turn it over here to Dan.
Hi, everybody.
Can everybody hear Dan?
Can you hear me?
Let's see. Okay, yeah, we're good.
Okay, excellent. So, pleasure to be here with everyone today. My name is Daniel Strano. I'm lead developer of the VM650TQ Qrack quantum computer simulation framework, along with Ben Belay. So today I want to start with a mission statement for Qrack. We're going to cover a layer chart for the general transparent best general use case stack. We're going to talk briefly about optimization theory that Qrack uses for what I call its novel optimization layer, or QUnit in the API. We're going to talk very briefly about some preliminary updated benchmarks, although we also have some that are not quite as up to date on our documentation that I'd like to refer everyone to as well. And we're going to finish with a couple of demos that I think are going to be fun.
I'm excited about the demos.
Yes, the demos should be colorful and fun. We've got one of them's in Unity actually, but what is VM650TQ Qrack? As those enthusiastic or involved in the quantum computing community, we know that there are potentially some scary new conditions that can arise from the technology. We realize that part of the reason we're interested in quantum computers is that they could pose challenges to encryption as we understand it. And we could potentially be looking at the end of private electronic citizen privacy as we know it, as we transition to better ways to handle it in anticipation of when quantum computers are coming. We don't know exactly how fast the timeline for these technologies is going to evolve. We have Peter Shore in Nature saying that we have to be vigilant. We have to be aware that people, certain actors might have exclusive access to these technologies, could be very soon, and we have to prepare for what's going to happen there. I think it's great that we have a kind of a centralized but distributed to an extent access to actual quantum hardware prototypes from companies like Amazon and IBM. I'm very thankful for everything a lot of these big players are doing to embrace the open source community for quantum computing and to make their hardware platforms available. But where Qrack comes in is we want to decentralize access as much as possible. We want a simulator framework that works with the maximum possible hardware and software. So Qrack already works with Linux, of course, but also Windows, Mac, and Android at this point. We've tested on Android. We work on systems back to not back to, but as simple as the Raspberry Pi 3, including the GPU of the Raspberry Pi 3, since someone was cool enough to kind of make a thesis project and a labor of love out of OpenCL ICD for the Raspberry Pi 3. We also work on the 4. Hopefully we should work on 32-bit systems. And the joke goes, I'm sure we're all sick of it, but we literally want to run on a toaster if your toaster runs ARM. But
I want to simulate qubit. Like, is that still annealing then?
yeah, good good question. Good question. It's it's what we're trying to do. I don't know if there's much use to being able to run quantum computer simulators at the moment on your Android phone, but maybe we need it, and it certainly, I hope, removes a barrier to access to fast quality technologies. So we're going to start with a layer map of what makes up kind of the general optimal use case of stack. We call them engines and layers in Qrack. But so at the earliest stages of the framework development, cat simulations seem to be most obvious. Cat in the sense of the Brett-Cat notation of Dirac. These are the simulators that you most commonly have seen for a very long time. It's the simplest approach. I think I can say it's also known as Schrodinger method sometimes. But we wanted to have a totally dependency-free version of the simulator that could run on hopefully just about any system that there was any demand for. So that would be the QEngine CPU, which is a pure C++11 standard implementation. It has one internal dependency. We use catch Clara for unit tests, but 0 required external dependencies, pure C++11. Then we have QEngine OCL, which is OCL is OpenCL, which is GPU accelerator based on OpenCL. I mean, it uses OpenCL. It works back to version 1.1. At this point, we've also tested with multiprocessor out here at the QUnit level, which I'll go into in a minute. But QEngine OCL has been tested with Intel Core, Xeon, HD, but also NVIDIA. And like I mentioned, even hopefully we run on anything that there's an OpenCL implementation available for including like the GPU of the Raspberry Pi 3. So the QEngine CPU seems to be efficient for low numbers of qubits. It seems to have a certain edge over the GPU case for small numbers of qubits, where the number of amplitudes that we have to vary in the course of a gate don't necessarily even cover the width of a GPU, which might have thousands of processing elements. And so eventually, way down the road, we successfully hybridized the two of them, as I call it, where transparently you can switch off between CPU and GPU implementations. If you cross a qubit threshold, you're automatically using whatever's appropriate for the numbers of qubits. Those parameters can, yeah.
So we got a question from chat. Keyhost asks, does it also support distributed simulation like via MPI?
So we don't use MPI specifically. We actually use C++11 futures for the QEngine CPU. And so there's a threshold at which it's not it's more efficient to batch small numbers and dispatch asynchronously. So QEngine CPU up to again a small qubit width will actually just batch everything together in a single asynchronous thread. and there comes a point that we've tuned, we've figured out, but it can also be controlled with runtime and build time parameters, where the CPU will do parallel simulations rather than asynchronous with futures. But the benefit of this is that you don't need the MPI dependency necessarily. It would probably be widely available, but it's what we've done so far. I don't know that that answered the question. uh, but we also we also do have some handling for multi-accelerator GPU via the QUnit layer, which I'll explain in a minute. That's our novel optimization layer. But basically, QUnit maintains it looks for separable subsystems or tries to proactively maintain subsystems of qubits as separable per I'd refer to there's breaking the 49 qubit barrier by Pednolan and team at IBM. And I'm sorry if I mispronounce anyone's name, but I read the papers. I don't necessarily hear the name spoken. But we use Schmidt decomposition, this concept of Schmidt decomposition, to keep subsystems separate, and these can be the subsystems can be distributed to multiple accelerators like OpenCL accelerators. So I hope that answers the question. So moving on, if we've got these KET simulations, which would be CPU or OCL and hybrid. And recently we've started experimenting with stabilizer, Clifford set simulations. And again, we wanted a transparent switch off between stabilizer, which has an API limited to Clifford gates, basically. And we wanted to be able to immediately switch over to KET as necessary if someone uses something in the more general API that can't necessarily be handled by stabilizer. So Q stabilizer is basically a C++ port for our purposes of Aronson CHP. And we bring this together in the Q stabilizer hybrid, which can handle both stabilizer and KET. Insofar as you're doing Clifford simulations, it should give good, as we would expect for Gottesman-Cannell stabilizer simulation, and it'll switch over to KET without any hassle. Just use the gates you want, and it'll immediately switch over to KET as necessary under the hood. So we bring this all together under this QUnit layer. And we also have the QUnit multi-type, which, as I was explaining, it allows you to use multiple OpenCL accelerators for subsystems. But QUnit maintains separability. It proactively looks for separability of subsystems. And I can explain how with my next visual here. Let's see. So sorry for the text, but it's only a blurb here. Qrack optimization. So I think the Dirac notation is helpful for this, and it's good to see it written out in actual Dirac notation, I think. But suppose we have an initial KET AI and a tensor network B1 that maps it to a final KET AF1. So as equation 1 here. It is tautological that if any other tensor network B2 maps the same initial AI to a final KET AF2 as equation 2 here. So we have B1 acting on AI producing AF1 in equation 1, B2 acting on the same AI mapping to some state AF2, but also satisfying the condition that AF1 and AF2 are identical in the expectation values of all Hermitian operators. So basically just square norm of the inner product is 1. Usually we would say these are the same state, to put it more simply. but in terms of the bookkeeping and the amplitudes, it could be up to phase factors that make no difference in the value of Hermitian operators. That could be global, but it could also be subsystem phase factors. Then one cannot distinguish B1 from B2 only by knowledge or measurement of any physical observables of AI and AF1 or AF2. Any such B2 can be substituted for B1 without changing any measurable quantity of the end state, at least in the specific case of AI. So to decode the jargon, QUnit couples actively in time. It couples its optimizations to the active state of qubit registers, and I have some examples to show on the next page for C0. But rather than just talking about the symmetries of the tensor networks and looking for tensor networks that are equivalent in other ways, all we really care about. Yeah, hey.
Can you increase the font size a little bit? Thanks.
Sure. Sorry. Okay. So also we can relax the condition for a known particular basis of measurement for the final state. This necessary and sufficient condition for equivalence of physical observables can even be relaxed. And here we have the basis expansion in this inner product. We bring the summation outside of the square norm, and we're basically just saying if we know the basis of measurement, all we care about is that all observables are the same for that basis of measurement. So sorry for the text, and by the way, I can make this couple of pages available. I can maybe I can get that to Sarah, or I can have it linked through the Qrack repository. But I have a couple of examples here to make this a little simpler and concrete, hopefully. So for one example, say we have the C0 gate, and we're trying to figure out how to maintain maximum separability. Is the C0 gate necessarily entangling in this case? And QUnit will actually introspect in ways that we've tested and found to be efficient. And if the control bit of the Q0 gate, for example, is deterministically false, so it's an absolute zero qubit, it's not superposed, then C0 can be replaced by identity, because since the control bit is zero, the gate doesn't fire C0 at all, and in this case, our ket remains the same either way, whether we're applying C0, which would usually assumed to be an entangling operation, or whether we just simply omit the gate entirely. And in either case, we end up with the same end ket here, whereas example 2 would be a control bit is deterministically true. Okay, in this case, the gate absolutely fires its payload of the poly-X, and it need not, again, necessarily be an entangling operation. If deterministically true control, the control bit remains true, and we can think of this as C0 can be replaced by poly-X on the target bit. So here we have the C0 gate. Here we have a poly-X Kronecker product on the X is acting on the low bit, which is the target bit in this case, in both cases, and we end up with the same end state in either case. So again, I think what I can emphasize here is that what I haven't necessarily seen done in other simulators that QUnit does here is that we're coupling to the active state of the qubit register in time to look for our symmetries for replacement of gates or tensor networks. We can recover quite a bit of separability this way. Basically, for every qubit, we peel off the bulk of the simulation into a separable subsystem. It's roughly a factor of 2 RAM and speed, as probably makes sense to most of the room in terms of what we usually call the Schrodinger method of simulation. So how well does it work in terms of performance? So I want to point out we have some performance docs on our documentation. We've got Qrack read the doc
Can you
stuff.
zoom in a little bit on this?
Yeah. So these are from a few months ago. Here's where our n-qubit QFT was. I wanted to show an updated graph of the QFT from the past week based on recent work, but I'm in the process of updating these on the Qrack performance page in our documentation, and those are a good reference that we're updating at the moment. And I wanted to show where are we? Okay, so here's from the last week or so. We have comparison between CIRC, which is the Google unofficial Google quantum computing simulation framework that's CPU based. We have QCGPU, which is another OpenCL and Python simulator, and actually another recipient of a Unitary fund grant. And it's been cool to see what QCGPU has done. Qiskit, which is the IBM framework, and we're benchmarking CPU in this case, whereas there is a GPU mode available to Qiskit at this point. I just haven't finalized my methodology for benchmarks on that yet. And we have Qrack, which is the purple. We call it GPU based here, but again, this is kind of the hybridized CPU GPU. Footnote, this is Ubuntu 18.04 on AWS machines. GPU was benchmarked on an AWS G3S X large, which is like I think the tiniest GPU enabled box. CPU benchmarks are AWS C5 4X large. And what we aimed for here in selecting the instance types was trying to maximize, performance per cost of, time running the AWS instances. But we can see here that on the G3SX large, for example, Qrack gets a particular efficiency bump up to about 10 qubits. That's probably where CPU. This is probably actually asynchronous CPU, but the benchmarks account for the full time. But this is the asynchronous mode of the CPU. This is where we switch over to GPU. CIRC and Qiskit are ahead for a little bit here, and ultimately, as it shakes out at the high qubit end, Qrack pulls ahead. This is on a logarithmic axis here. That usually seems to be most appropriate, as we know that the scaling of resources and execution time tends to be exponential for simulators.
So Will from chat asks, is there a gradual notion of approximately separable that can be used for faster approximate simulations?
We use an exact approach to the point that I even attempt to avoid float rounding error. We actually use a lot of direct checks for zero floating point equality. If there is an approximate notion, I'd love to see it developed, and I'd love to, please, anyone feel free to pick my brain about it. But we've dealt with exact, and I don't have a concept of approximate separability yet. I know that when I say proactively maintain separability, I know that separability, the so-called separability problem of taking a quantum state and determining after the fact from full expansion in terms of the amplitudes of Schrodinger's wave equation to determine whether it's separable after the fact is considered a hard problem. It's exponentially scaling resources to determine that. So QUnit will start from a state of initially every single qubit in the QUnit will be a separable single qubit simulation. rather than try to separate things after the fact, we try to move along in such a way that we recognize this next operation will not entangle, so we'll stay separable in this case. I wish I had a better answer for you, Will. No, I don't have an approximate notion of separability yet, but again, I'd love to help with one if anyone would like to pursue that.
Uh, yeah, no, definitely. And so KeyHost also asks, what's the largest number of qubits you've been able to simulate?
Well, okay. Actually, there are totally trivial cases. For example, like with zero separability, just using single qubit gates. But this probably isn't what you're interested in. But just using single qubit gates, we could go almost arbitrarily high. Base build parameters will get you up to 64 qubits in width for a Q unit. We have an optional dependency on the boost big integer library where we're actually kind of dependent on our largest integer type for mapping qubit width in an engine or a Q unit. So using boost big integers, you could go not arbitrarily high, but you could try up to probably a few hundred qubits in width. But typically for general use cases, by the time we get to anything interesting, the separability gives a bit of an edge up to a point, but we are still ultimately limited by the exponential explosion of resources. And on your typical 32 gig machine, 1632 gig machine with 8 gigs of graphics processor unit RAM. 27, 28, 29, 27 for a lot of GPUs at 8 gigs float accuracy. I think that's right. So I mean, you can experiment with limited cases of going further under cases of really high separability, but for the most part, it's still limited by the exponential resource explosion. So do we want to move on to demos?
Yep, that sounds good.
Oh,
I'm just
okay.
trying to be real
Okay.
careful with all my mutes here.
First one, we're going to go with the one I think is more fun first. They're both fun. Quantum computing is all the quantum computing is fun, but so we've actually integrated Qrack into Unity. I maintain a fork of the Open Relativity physics module for Unity by the MIT Game Lab. I started working on that back when I didn't really have my feet wet with GitHub, and I hope I didn't totally explode notifications on the repository, but it was a lot of fun working on it, and I've kept up with it since. If the package manager would start, there we go. But we've incorporated Qrack. We have a DLL that we use for Q#. So we're actually also available as plugins or NuGet packages, not yet distributed, but the source is available for Qiskit and Q#. And the DLL that we use for the Q# simulator interface, we can also use for Unity. So this is kind of
just
my
so I can
demo.
understand, you have so you can write front end code in Qiskit or Q sharp, and this plugin in Unity will consume that and then use Qrack as a simulator for that.
Those are
Or those are separate.
separate.
Okay,
Yes. What the tangent I was kind of getting off on there is that the DLL that is useful for the Q# integration is also useful for a plugin for Unity.
gotcha.
But so these 3 boxes at the back here, this is sort of the general sandbox for new effects. I'm trying to add open relativity, but the boxes on the far right and far left here, these two are actually performing a quantum teleportation algorithm with Qrack. It's not the best visual for it, and physically we wouldn't see this happening in terms of, totally non-ambiguous macro state of the underlying quantum state. But the box in the middle is doing the same for triplet oxygen simulation. But the three axes of rotation of the boxes are the three axes of rotation of the Pauli axes for qubits, two-state system. And this is actually, length contraction and time dilation are handled, and speed of light delay from box to box. So depending on where we look at the systems within the space, we'll actually see different delays between the boxes, but hopefully staying causal, local.
That is so cool.
But
So the like what we're seeing here actually takes into account the speed of light for the distances between
yes, it
stuff. That is
does.
so cool.
Thank you. Thank
Physically
you. I
realistic
hope,
games. I can appreciate that.
yeah, I could appreciate what the MIT Game Lab did here too, and I'm very appreciative to them for releasing their module open source and letting me tinker with it. But I just thought, hey, our open, relativity and quantum mechanics, it's like chocolate and peanut butter,
That is a good combo. Uh,
So
cool.
so this is available to play with on my GitHub. This is on my personal GitHub. There's the VM650TQ Qrack organization page, and then I'm Wrathful Spatula. But this is my fork of Open Relativity on GitHub.
So is there a story behind your GitHub handle, or uh,
It goes back to a handle I've had since high school, and people have known me by it. I think I signed up for a GitHub account ages ago, and it was like I don't really know what I'm doing with this. I'm just gonna put my internet handle from high school, and I've noticed that a number of people seem to do similarly, and I don't have the heart to change my handle at this point.
I can understand. Mine everywhere is crazy for pi 314. So that's
Yes,
that was
I
also my
love it.
first internet username, and
Mhm.
it stuck. Okay, so cool. So what you so just to kind of clarify, there you can use Qrack as like you can simulate things in Qrack and have that interact with kind of the mechanics of what's happening here in the physics, right?
Yes, correct. I have a couple of classes in there for examples like these. I have like Teleport Alice, Teleport Bob, but I call it something like Real Time Chasm or
Mm.
something like that. It's not really properly, but the idea is the scripts that are already there should be a good stub such that you can actually hook operations on the quantum computer simulation onto the world clock of the world frame in this case, since it's relativistic
Makes
and
sense.
there's no. Yes, yes, but you can hinge the operations on the world clock of the game clock, or you could use the plugin for high performance computing in Unity
Mm.
that doesn't necessarily have anything to do with in-game quantum computing. But I thought it was cool to have some in-game quantum computing,
Oh yeah.
particularly yeah, particularly in the spirit of the Open Relativity project.
Mm-hmm. Yeah, I imagine
All
this would
right.
be a good resource for folks doing some of the game jams or quantum game jams in the future.
Yes, absolutely. It's MIT licensed, so by all means play with it to your heart's contentment.
Sweet.
Yes. So there's another example I wanted to show. Did we have any more questions on this demo before I close it and move on?
Not that I can see so far.
Okay.
But yeah.
Okay. Okay. So the other example is not as colorful and video gamey, but we have here. Let's say. Um, so part of the original thrust of the Qrack project was to create chip-like quantum computer simulations,
Can you
and
make the
one of our
text bigger?
Yeah, sorry.
Nope, this
Sorry.
is usually I always have to remember
Uh,
this too when I'm screen sharing and stuff. Uh,
okay. So this is unfortunately this is as helpful as assembly, but it's actually it's basically 6502Q rather 6502 MOS 6502 assembly. But we're going to run this in VM6502Q, which is sort of the namesake of our our organization page on GitHub. But we created a superset of the MOS 6502 assembly language. There was one unused flag in the 8 bits of flag on the MOS 6502Q. Oh, I should absolutely mention the simulator we're based on is by Merrick Karks. Again, I hope I pronounced that right, but we're really thankful to him for the 6502 emulator. I picked that one because it's open source and I thought it had some of the best interface and in my opinion seemed to be one of the best all around MOS 6502 emulators. The 6502 has been used in systems like the Apple IIe, I believe. I think the Commodore 64, and it's actually also the processor. To bring it back around to video games, it's also the processor in the NES the original NES Entertainment, Nintendo Entertainment System. That chip's actually the 2A03, which has additional embedded systems, but the CPU itself is the 6502.
so
So
let me just see if I can summarize and that I'm following here. So you have an emulator that is going to emulate, the type of chips that you were just talking about that are in the Apple IIe, the NES systems. And this is an
right,
instruction set that's actually an expansion of the original instruction set so that you can include quantum instructions as well, right?
correct,
Gotcha.
correct, and all of the existing instructions should work to an extent in a way that made sense to us with active qubit registers. Basically, the registers of the chip itself are treated as qubits in general, but we have this load A X instruction. But let me get up so we're going to be running Grover search. This is in location 00C 0C00, and we're going to be searching for the value 100 or a hexadecimal 64, which is in position E6 in this classical table of pages of values at memory location 0F00. And Grover search should find this location. Let's take a look at here. So the emulator has this
Can you
awesome
also make the,
disassembly.
the terminal big?
I hope I can. Let's
I mean, even if you
see.
potentially can you just maximize the window or something?
It tends to do that if we
I see.
max.
Okay, there. I think that works.
Okay, is that
Yep.
hopefully? Um, so has this awesome disassembler here. It's a little difficult to show what's going on in the registers while they're in superposition qubits. But if we go to address 0C00 where the program starts and we start to step, we've got a clear Q, which is clear the quantum flag, which is this flag actually doesn't exist in the original 6502, but we have our Q for quantum here. We've got a load X that just clears the state. We're loading our Y for iterating for Grover's search. These are flags, but it's this load A instruction that's kind of specially quantum, and so the idea is that we have the X accumulator, not the accumulator, but the X register here is in a superposition. It's showing 8-0 here, but it's actually in a superposition of 0 to 255 via Hadamard gates across the register. And this X can point in superposition to a page of memory. So is this physically realistic? I don't really know, but the cool thing about the concept is that it's unitary. We can load in a unitary manner this way, and we don't entangle the classical cache of RAM.
That is
The
so cool.
concept could be one, yeah, the concept could be one of like we take a cache of classical RAM, could be superconducting, probably would have to be superconducting. We could maybe put it in the cryovac with the qubit registers themselves, the actual quantum processor, and hopefully by superposing a load offset in this X register, the idea is that it's at least unitary that we could load in superposition from that page without entangling the classical RAM. Again, as to whether it's actually physically hardware realistic, we're not really concerned with it. But if we just this loops for 12 iterations of Grover search, and if we just continue, it should go until a break point. And if we hit the step again, so we have a break, and we see that the accumulator's reading 64. So we did 12 iterations, and we found the hexadecimal 64, which is value 100, which was entangled with the X value, which correctly found our index of E6 in the page that we had offset into. So the X register and the accumulator during thank you.
It's always good
The
when a
X
Grover
register,
search finds what you were pointed it
it,
towards.
it always is. Yes, it is. And it doesn't necessarily have to do so. Yes. But so when the X is in superposition, the entanglement that we do have is between the accumulator that holds the value of what was in that page and the X register that where each value in the page is entangled with the index and the X register for the offset. So that worked.
Yeah,
Yeah.
that is awesome.
But yeah, those are basically my demos. But this is available. This is VM6502Q on the general VM6502Q organization page, and everything we do is either LGPL or more permissive in terms of the open source licenses. And I forget, it could be that VM6502Q is still technically under GPL, but the open relativity example, for example, is still that whole module is MIT licensed, and I'd be very happy to see people adopt it and use it for their own ends, whatever it might be. But those are basically my demos.
Those are super cool.
Thank you.
I am especially intrigued. Like, so yeah, the second demo, basically you kind of have this mental model of a device that can consume the 6502Q like assembly instructions, and it could do quantum sorts of things, right?
Yes.
And so, like, ideally, like here we're emulating it, but as you were describing, like, we could do something, or it is possibly conceivable, though not proven, that, a
Hopefully.
chip, we could have a chip that would actually consume this, that would have, say, superconductors or something like that on it.
Yes.
And then
Yes.
you don't have to worry about like this classical register being in superposition. um,
Right.
but
Yes. I think we'd all love to say it'd be the same. But it's much easier to simulate or emulate, and again, we mostly just concern ourselves with whether or not the operations are unitary except for measurement. When we have an accumulator in superposition, if we attempt to write to the classical cache in the VM6502Q model, first thing we do is collapse the register. And then we write whatever the measured result of the register is to a single location. We also would collapse the X for the offset, and we write it to a single location. Generally, it wouldn't be an intended use case. And if you think about it, if we were to try to write, say again with a superposed offset register for pointing to the classical cache. If we were to attempt to write that, we would become entangled with the classical cache necessarily, no matter how you do it, if it's even feasible. And that becomes very susceptible to noise. And if we turn anything off, we presumably end up collapsing into a single state of the classical RAM cache in that case. So it's not really practically feasible. We just collapse the registers before we write to classical cache in this case.
So we got a good question from Kiyoshi again. Can Dan comment on the roadmap that IBM has with respect to the how many qubits in a physical quantum computing device that they'll have in the next couple of years? Like basically, do you believe what they say? Is what they said.
Um, I haven't seen the most recent roadmap, so I can't speak directly to that, but I can tell you that I've heard a lot of the general announcements and earlier roadmaps out of IBM, and I think they have the right idea in general for a long time. I don't, I think they're neither being overly pessimistic nor overly optimistic. It seems reasonable to me. I think I've heard out of them that we're probably looking at a gradual ramp up to practicality of quantum computing, not necessarily a slow, an immediate breakthrough moment where suddenly quantum dominates everything and completely displaces classical computation for high performance computing purposes.
What? Quantum
Again, I
computers
haven't.
won't replace everything?
I mean, it kind of might be awesome if they could, but I think it is going to be a gradual transition. I've noticed, I make a joke about it, but I'm halfway serious, that as far as the simulators go, we talk about so-called Nevin's law, of doubly exponential rate of growth of the power of quantum computers. I've noticed that it seems like the simulators themselves over time seem to have kind of a rough doubling behavior in terms of the software, where the software gets better, excuse me, giving kind of an exponential growth of software efficiency, whereas for the time being, at least, we're still undergirded by Moore's law, such that we get kind of a doubly exponential out of the progression of simulator software with underlying Moore's law for the time being. So I think IBM has been right in the past to say it's going to be a slow transition where we reach not immediate total displacement, but gradual areas where quantum computers are good, that we're using them practically.
Yeah, they put that the current roadmap says 127 qubits by 2021, then 433 by 2022, and then 1,121, an oddly specific number, in 2023.
I
So yeah,
I I can't really
yeah, no.
comment on too know, like it sounds reasonable. I would basically trust it, but we know that the timelines do get amended. IBM seems to again not have so far been overly optimistic, not fallen into that trap, nor have they been particularly pessimistic. So
Nathan has a question. So, as they say, a high level question. They understand that you, Dan, do not work full time on quantum computing. So, how do you kind of make space and and time and possibly entangle, disentangle resources for you to work on quantum computing stuff?
yes. Um, so I mean, the simple answer basically is that, like, it's kind of a joke, but it's kind of not. Television kind of bores me. After a day of work, I find it entertaining to come home and work on VM650TQ Qrack, or in the age of COVID, basically just switch from my work laptop on one side to my personal laptop on the other side, and immediately switch over to uh, programming the stuff that I find fun, and it's probably not the healthiest attitude in reality, but it's just it's what I like to do. It's at the time that I found to do my projects for VM6502Q and my general GitHub. That's where it comes from. So I don't necessarily have a better answer for you, but you know, if you find yourself bored buying social media, like I think we've probably all had a bit of an overload on social media in recent times, and you know, sometimes it's just turn it off. I don't really, you know, it's just what I like to do.
How do you find maintaining an open source project? Like I've recently kind of gotten into this myself as well with some Q# projects and stuff like that. I had never really done any like I'd contributed to open source stuff, but I hadn't really kind of taken on that role of maintainer. So like how how do you like it? Like where do you think you spend the most of your time for folks that maybe aren't familiar with that?
Yeah, well, I'm kind of benevolent dictator of of Qrack, so it's been easy in that regard. But I'd love to see, you know, more community involvement. We do have a friend who might be watching who has been taking it upon himself to do other benchmarks for us and package us into you know, he calls it CrackNet, which is a Dockerized container that he's experimenting with, like FPGA and bare metal
I love
and
Docker and I like these things that you're
yeah,
saying. I am very
yeah,
interested.
yes, his GitHub handle is two bombs, and he's actually become an important member of the team, and I'm very appreciative to him. But he keeps the enthusiasm going, and he seems to be cool, doing cool stuff with us. It's largely on his experience that I do some tuning of the multi OpenCL processor modes of operation, because he claims to get performance boosts there, and insofar as I don't really personally have that hardware, and I have limited, I do have access to it, but I have limited access to it through the cloud. It's great to have community involvement, and we want to have a lot of community involvement. You know, by all means, even if you have a general question, I know this is new material. I'm not going to be the kind of person who, if you open an issue for a general help question, we might still refer you to the docs, but hopefully I could give you an explanation of exactly what's there in the docs, and why that makes sense, and have a discussion with you about what we do and how to use us, and anything you want to contribute, we'll open a pull request. So
Yeah, definitely.
uh,
Like one of the our goals here at so Unitary Fund, we fund a lot of open source quantum software projects. And one of the things that kind of this talk series that we really want it to come out of it is folks to like learn about other projects that are out there. And maybe if you are interested in contributing, or, you know, like working on maybe something for if you're a student working on something for your thesis or something like that, and you're like, hey, maybe this would be a good piece to add here, or maybe I could actually use this for research. Yeah, I think I find it's always helpful to put like a face and a person to like a project,
yeah.
so that you can kind of both learn about the project and also, you know, realize it's not just kind of like a autonomous code base that then when you get angry know that there are people there to help you with it. So
Yes.
um,
Yes.
Nathan also had asked, what are your suggestions to folks who want to kind of get into doing some quantum open source stuff, like especially if, as probably a lot of us are, you know, quantum isn't necessarily our day job. So like, what would you
Understood.
suggest?
Good, good question.
Obviously, read the
It's
crack
not.
docs and see what you can contribute.
Yeah, obviously, you should use us. You should come to us, and we'll set you exactly. No, I mean, I found that a great way to get involved was to you know, try writing your own simulator. Believe it or not, as I you know, direct you away from just using us. But it's a great exercise to write your own simulator, and it's not particularly hard. The Microsoft quantum katas seem to be pretty popular. there's unfortunately, the resources are coming along, open source, like on the high performance end, but also on the teaching end. And there seems to be a lot of that out there. Awesome quantum computing. That list, I don't have a link for it here, but if you look at the quantum computing resources lists, those are on GitHub. Those are great places to start. Again, just trying to build a simulator, trying to build a simple simulator is a great practice. One of my favorite books, which is useful for both computer science and computer scientists and people coming from the physics side. It's a bit dated at this point, but it's still a great reference text, is Quantum Computing and Quantum Information by Nielsen and Chuang. It's still a developing field. And I find that I've been saying to people lately and for some time that it's still, it's still up in the air to a certain extent. We don't necessarily know all of where this is going to go, what's going to be useful. And you can get involved in research to a certain extent, even if you're a citizen scientist like me, basically, where experiment. Just think of something fun you want to do. The VM6502Q project. Originally, I joked with Ben that I want a quantum computer simulator that plays chess. And VM6502Q, he laughed at me, by the way, but no offense taken. But will actually microchess will hopefully actually run on VM6502Q. That's like one of the earliest computer chess programs from like back in 1970s or something like that.
I feel like that's in the same tradition as like trying to get Doom to run on the Windows Process Manager.
Yeah, exactly, exactly.
What can we get to run somewhere it really shouldn't?
Yes, yes. There's a great Saturday morning breakfast cereal comic about that. The alien computer that the computer scientist is like the architecture of this machine is like nothing I've ever seen. We have much to learn from it and perhaps much to fear. And then it says computer engineer, and it's like bam, got Doom running on it. You know. But experiment, like play with it. Maybe play with our Unity plugin and make a video game with it. By all means, the community could use it, and your scratch work could be helpful to someone else who's following along just behind you in learning about quantum computing. So I wish there were kind of more centralized resources I could direct you to, but there's a lot of opportunity. You got to poke around a bit, though.
Folks in chat have been putting a bunch of good resources, so definitely, I think
Awesome,
we've got
awesome.
some lists to like the Quantum Open Source Foundation has some good resources.
Yes, absolutely.
The
Yes,
awesome lists. There's awesome quantum
yes.
computing. But and then a Nielsen blog post as well. But definitely check those out. I'll make sure to copy like all of the links and anything that we've shared in chat today. I'll definitely have on our Discord as well. And Dan is on the Discord. So if you have like further questions, there are a couple more questions though here. But I'm not trying to wrap up. I'm
Okay,
just trying to
okay,
remember to make those
sure.
plugs. So one other question for Dan: are you interested in making your simulator also work with multiple servers at the same time, or is it not worth the effort with respect to the exponential increase in resource requirements?
So we've actually already experimented for multi-node, multi-server, multi-accelerator with SNUCL. So we're actually compatible back to OpenCL v1.1 standard. We use, I think, one optional feature of two, v2.0, and we check whether or not it's there. And if it's not there, we don't use it. So I've tested that in proof of concept. Yes, we will run on like SNUCL, for example, and that's publicly available. cluster resource. This is still new territory for us. We're absolutely interested in it. Our focus has definitely been again more towards how far back can we go? C++11, can we get it to run on a pure 32-bit system? How small and simple can the hardware be for a quantum computer simulation? But we definitely want to grab both ends of the equation, and we do intend to continue expanding the multi-accelerator and cluster functionality. Yes.
I mean, I do want to reiterate here, like, Qrack runs on Raspberry Pis. Like, that is so freaking cool.
Thank you.
And totally also agree, kind of maybe going back a little bit to your earlier comment, building a simulator, I think, is a really good kind of introductory exercise. Like, pick your favorite language, like, or platform, whatever it is that you are comfortable and try to figure out how do you do matrix manipulations? How do how can you implement a simulator? And I think that because even if it's not the world's best simulator, it will likely not be as fast as Qrack. But
I hope it is. Yeah.
nah.
I'll use
Yeah,
yours.
yeah. But yeah, I think that's a really good way to kind of learn, especially what that interface between the classical computing pieces and the quantum, like, because obviously, the advantages we can get with the quantum hardware are great, but if we can't like translate or it's that IO interface layer that is, I think, really kind of critical to understand and explore. And that's why, like, I think it's really cool to see projects like this where we have a kind of faux chip that is a quantum chip, and we have this instruction set for it that does support everything that we could do for quantum computing. And I think it's a really neat way to kind of use paradigms that we're familiar with and map
Mhm.
it to kind of new hardware that I mean, I do like the accelerator like model for quantum computing, of thinking like a quantum computer as like a GPU or like an FPGA or something like that, where you're going to send a specific subset or subroutine to this device, and then you kind of everything else is like normal.
Yeah.
So,
Yeah. I like both models as well. Qrack, we also have a plugin for
mm,
XACC, which I should definitely mention because I really like that project, and I've talked with that team a little bit, and I think they have a great
mm,
model. The accelerator model makes a ton of sense to me. Obviously I'm coming from OpenCL. QIR. Sarah and I were talking about QIR a minute ago before the stream started, and I think that's a great approach. A chip like QCPU, so to speak, a quantum central processing unit, kind of made sense to me. 3 years ago when I saw Q Sharp, the first release of Q Sharp, and I was like, I want to write a simulator, and I'm going to write it in a way that makes sense to me. Um, it can be open ended. It should be unitary.
that's exactly right. Everything,
Yes,
because everything
yes,
evolution is unitary. That's the Unitary Fund
yes,
tagline. In case
yes,
people didn't know.
yes. It's a wonderful tagline.
Sweet. Well, I'm just gonna look through chat real quick to see if there's any other questions. Nathan said, "This is Dan. Dan gets bored by watching TV. Dan builds fast C++ emulators of quantum computers in the spare time. Be like Dan."
Thank you for that. Thank you for that. I got to steal that.
And also, Two Bombs did say hi, so
Oh,
yeah,
excellent, excellent.
definitely.
I'm glad you tuned in.
Thanks for hanging out, and I definitely want to check out the Docker stuff. So
Yeah, yeah,
that'll be pretty
absolutely.
cool. Well, great. I want to thank everybody for in chat who's hanging out, and hopefully this was useful, and hopefully you'll check out Qrack. Let me put the link to the project one more time, real quick. But yeah, if you have any questions, certainly like file issues, like do the
Absolutely.
normal open source interaction stuff on the repo, and like
Yeah.
if you have more, like you just want to talk or something like that, Qrack also has a Discord, right?
We
Yeah.
do, we do.
So
The link is on
it's
our.
in the
It's in the
README, and I
README.
also just put it in chat.
It's in the
So
README.
yeah, everybody can
Excellent. Thank you.
kind of interact with the Qrack team more broadly, and certainly if you have more like general or want to chat with Unitary fun folks, we also have a Discord. The URL is just Discord. Thank you, Will. Discord.unitary. Very there we go. But yeah, feel free to drop in and ask whatever questions you have, or maybe you want some ideas for where to start with projects. We're always happy to help with that. And yeah, connect you with different cool open source projects like Qrack. Um, Great. Well, thank you again, Dan, for coming and spending some time. This I guess it's over your lunchtime, hanging out, and yeah, I look forward to. I actually really want to try it. I'm not very good with Unity, and I haven't really done much there, but there's enough really cool like quantum plugins or interaction stuff, and I have like some ideas for a quantum game that I think could be like that's
Awesome.
always been like, oh, how do I actually get that into a game engine? Well, now it's there, and so I just need to
That,
learn how to use Unity.
yeah.
So,
Yeah, make a video game. That's a great idea
mhm,
for a project to get your feet
yeah,
wet, for anyone. And Sarah, thank you, and thank you for everyone for tuning in. I really appreciate the opportunity to talk, and the questions are great. Please open issues and or PRs or whatever.
Dan wants issues,
Uh,
folks. You heard it here.
yes, give me issues. Yes,
He doesn't want to watch TV. He just wants issues.
yes, yes. Coding in anger.
No. Makes sense. Cool. Well, yeah, tune in. We'll have another talk in December from actually Alex McCaskey, who works on. Do you pronounce it Zach or XXAC? I'm never quite sure.
I'm not sure. I'm not sure.
But yeah, we'll hear from Alex about the Zach. I'll call it the Zach project, and yeah, we'll be excited, and please interact or ask us questions on Discord in the meantime. But yeah, have a good one, everybody. Bye, folks.